right now. So configuration model. So this is very important. Again, something that was sort of developed in different ways, but Mark Newman did a lot of work here to sort of bring it into people's vision. So configuration model, or we can just say arbitrary degree distribution. Often we sort of use those words. And so we could generalize this construction, right? We're sort of really, well, let me just say this again. So we've got, let me go back here. So what all of this means is if we go to this box and we've got a large N, a large M, and we reach in, we pull out a network, and we do that over and over again, we'll always get one with a Poisson degree distribution, basically, right? We'll always get them. So, but we know the world is full of networks that, in fact, do not have that degree distribution. And in truth, I don't think anyone's ever really seen one. Like in a real world, large kind of messy network story, someone's, here's a network, of larks who talk to each other, or, porcupine somethings, phone calls. While Poisson distributions, as we sort of talked about, they appear a lot. That's a really natural kind of thing. In terms of Poisson degree distributions, I don't think anyone's ever really found one in the wild. So that's really weird, right? So the thing that we make this kind of randomness is a great thing, and usually, gets us a long way in describing the real world. A lot of the work we do, I think, in some ways can be thought of as like removing all the randomness until you find the structure, the shape of something. It's like sculpture. Anyway, you reach in this box, you pull out something that you don't see in the real world. And you do it over and over again, and you're like, what's wrong with this? This is crazy. So these are things that live in our heads, and we made them up. And nature doesn't do that. Nature makes things, right? They grow. And so these aren't easy to grow. And there are some nice thoughts about how you might grow them, but we didn't grow them, right? Callaway paper, yes. And pretty, so sort of naive models of how to grow a kind of random network will actually give you something that departs from these things. It's sort of hard to manufacture. All right, so that's all fine. I mean, we understand these things well, and they have a couple of really incredibly important things, like the phase transition story for the giant component. That's a huge deal. Like that's an essential story of, networks in general and how things spread and so on. That's an incredibly important thing. It's just not. It doesn't exactly fit the real world though. All right, so so these standard random, they have a Poisson ones, but we'd like to allow for arbitrary degree distributions. And so we can just do this in a couple of ways. One is to say, well, let's kind of let's sort of generalize the way we build things. Let's give these nodes weights, and then we'll make the probability that we connect two nodes, be a product of these two weights. And if we choose this weight distribution in the right way, then we can kind of really control the outcome. And so if all the weights were, equal, then we'd be back to where we were. Right? We'd be making these Poisson ones again. But so we're going to step away from constructing these things. It'll be actually more interesting to take real ones and mess with them. And also just say, this thing has this degree distribution theoretically, and then let's see what that means, right? If we're going to spread things and so on. Yeah. And of course, this is something, the power law size distributions or the heavy tail distributions, that's something that's, being examined to pieces now. Obviously, still people still have to tweet about it, but it's it's the rich get richer mechanism, which we've talked about a lot. Okay. Big deal. I'm pretty sure Marx understood that, actually. That's why we need taxation. Okay, all right. Actually, in that paper shredder discussion group, we looked at a paper that basically made that point. That said, look at all these rich get richer mechanisms. Didn't quite, right. Not quite a revolutionary document. Okay, let's see. So, so these are ones that have power law degree distributions, right? So these are going to be quite different. They're random networks again, though. They're random networks. We've just wired them up randomly and so on, right? Good. Need to talk a little faster. These are the largest components. So these things, now it's a completely different game, right? And these are much more like real-world networks, or many classes of real-world networks. Doesn't always pop out the right way, but there are these centralized hubs that have many, many friends, and some of those will have many, many friends, and so on. So you start to see kind of hierarchical structures. The average degree is quite low, right? There's nothing huge about these things. But you also see, because it's one of these, it's a rich get richer thing, you have the very wealthy in the middle in terms of friends, and then you have the serfs out here with the one friend, right? Yeah. What's the Ron Swanson line, right? Capitalism, isn't it? It's a method for sorting out who is rich and who is stupid, I think. Is that something like that?